Take the whole time. We'll take, I don't know, maybe like a half hour or something. And then we're going to spend time working on either finishing assignment 1. If you have assignment 1 to turn in, then you don't need to work on that. But I'm handing out assignment 2, so then there's time to get a start on that. I encourage you to take advantage of time that you're given while I'm here. Because little sympathy will be granted to folks who waste this time and then say that this assignment is too hard. Okay? All right. Assignment 1 is due today by midnight. You can turn in a hard copy today or put a hard copy in my mailbox or slip it under my office door, or you could submit on Canvas. Just check the guidelines for submitting online assignments. Make sure that you've got nice high contrast PDFs that aren't dark and don't just look like you snapped.
Use this as a cover sheet for online submissions?
Yeah. Yeah. So if you're scanning it, go ahead and scan that sheet as well. And then I have assignment 2 to hand out, and that's due a week from today. Before we start, are there questions on the set stuff that we did last time before we continue with sets? So we had just done, we looked at a bunch of like different operations on sets. We looked at some properties of sets. What we're going to do now is do a couple examples where we write a proof about sets. The first one's really simple, just to illustrate the idea, the concept of how we start writing a proof about containment. Writing a proof about sets is usually showing that one set is contained in another or that two sets are equal. And of course, if you're showing that two sets are equal, you're just showing containment in both directions. So the basic type of relationship that we try to establish when we're writing a proof is containment. And here's one example that's pretty quick. We'll let A and B be any sets contained in the same universal set. We're going to prove that A intersect B is contained in A, is a subset of A. And, I'm going to just up here in the margins, sometimes it can be helpful to just jot down a Venn diagram to get yourself to the I believe it phase, So if this is A and B, this says we're going to show that A intersect B is contained in A. Well, here's A intersect B. Does that lie entirely within A?
Yeah.
Yeah, right? So that's a good way to kind of illustrate or get yourself thinking along the same lines or along the lines that you need to make your argument. A Venn diagram is not a proof. So if you're asked to prove something and you just put a Venn diagram, that's like a 1, okay? So we got to write a proof.
I think the communication there is pretty good, though.
You think so?
Yeah. Very visual person.
Yeah. I mean, you communicated pretty clearly that you didn't want to write the proof.
Yeah.
So let's prove that A intersect B is contained in A. This will be almost immediate. Here's how we begin a containment proof. We let X, or whatever you want to call it, but I'm going to call it X, be an element of the set on the left, A intersect B. What does it mean to be in the intersection?
That means that you're both in A and in B at the same time.
Yeah, so then we get to say then X is in A and X is in B. I mean, look at where we want to go. We want to show that A intersect B is a subset of A. So when we start out saying let X be in A intersect B, where we're hoping to show is to say, well, we're going to show that X is in A. X must be in A if it's in A intersect B. And we're pretty much there, right? I mean, the fact that it's also in B is a little bit immaterial to our proof, but we know that X is in A, so because X is in A, that means that A intersect B must be a subset of A. So that's what I mean when I say this one was pretty immediate. You always start with let X be an element of, this set on the left or whatever, right? And then you're going to show, as soon as you say, then X is in, this set on the right, then your bet's when you're pretty much done. So this was pretty immediate. But we just got that from the definition of what it means to be in the intersection. We're going to do one that takes a little bit of doing. And you'll need probably, so this will take this page and then probably some space on the next page, which I'm feeling pretty clever since I've already written in and planned for that extra space for everybody. You're welcome.
Wow.
Yeah.
What a great one.
So the first thing you might notice is that in this example, we're going to prove that two sets are equal, right? So we're going to prove two things. We're going to prove that the set on the left is contained in the set on the right, and that the set on the right is contained in the set on the left. So we're basically going to prove that intersection distributes over union. So I'm going to, because I know that showing two sets are equal requires me to do two proofs, I'm going to just set that up. I'm going to let the reader know this is my plan. So we will prove two things. One will show that A intersect B union C is contained in A intersect B union A intersect C. And then we'll show that the right side is contained on the left side. We'll show that A intersect B union with A intersect C is contained in A intersect B union C. So now the reader knows that I'm going to be writing two different proofs. So for the first one, I'm just going to restate what we're proving. A intersect B union C is contained in A intersect B union A intersect C. How do we start a containment proof?
By defining X.
And how do I define it?
You lost me.
Well, what is special about X? Anybody, feel free to chime in. What do I need to be true? When I'm grabbing an element X.
It's got to be in one of the sets.
Which one?
Prove
A.
Nope.
All of them.
Not one of the three sets, but just the overall set that's on the left. This guy right here is a set, right? It's defined in terms of like these other sets and operations on them, but it's got to be over here. It's got to be an A intersect B union C. So I'm going to grab an element, an arbitrary element here. The only thing I'm assuming about X is that it's in there. And then we're going to make an argument and show that it's got to be in the set on the left. It's got to be in this union. Or on the right, rather. So let's let X be an element of A intersect B union C. And, that's actually not a bad idea to just state what we're going to do, So I've grabbed an element there. And I'm just going to say that we will show, this is our goal for this part, we're going to show that X is an element of A intersect B union A intersect C. Right? That could even be sort of parenthetical, but like that's our goal, right? So as soon as I get to say that X is there, then I'm done this part of the proof. So X is in this intersection. I'm seeing that this involves three sets overall, but really I've got two parts. I've got A, and then that's intersected with B union C. So if X is in that intersection, what does it mean?
It's in both A and C.
It's in both A and B union C. Right? So if it's in the intersection of these two things, it has to be both in here and in here. So we want to show that it's, let's just think about what it means you know, this is our goal, right, to get X over here. So let's think about what it would mean to be in this set over here. I want to show that X is in this union, the union of these two things. So I wanted to make sure, what does it mean to be in the union?
It's in between them.
It's
It's in both.
It doesn't, it could be in both, but it doesn't have to be.
it's in one of the two or both.
Yeah, one or
It
the
exists.
other or both, right? So remember with the union of like A union B, like that's like the both circles shaded. So I want to show that it's either in this intersection or this intersection. So far I know it's an A, and that's good, right? Because to be in either of these two intersections, you've got to be an A. So if I could place it at either B or C, then it would have to be in one of these two intersections, which is kind of what we wanted to show, which is kind of what we want to show. So we know that X is an A, and we know that X is in B union C. So let's focus on this part right here. Since X is in B union C, what does that mean?
It has to be in either B or C.
Yeah. Possibly both, but I know it's got to be in at least one of them. So one of those things is true, right? X is in B or X is in C. Let's just take it case by case. If it's the case that X is in B, keep in mind I already know that X is definitely an A. So if it's the case that X is in B, where can I put it? Where do we know it lives?
In A intersect.
Yeah. And if it's in A intersect B, then it's definitely in the union of A intersect B and A intersect C. So right now we know that if it's the case that X is in B, we've shown that X is in that set that we want. But it might not be the case that X is in B. So we have to consider the other scenario. It's possible that X could be in C. And so how's this part of the proof going to go?
It's the
Then it
same,
would
but
be-
replace B with C.
Yeah, A intersect C.
Yeah, so if X is in C, since I already know for sure it's got to be an A, then we could say X is in A intersect C. And so definitely it's in the union A intersect C and A intersect B. So look at what we did. We started with let X be in this set over here, and then we were able to say without a doubt X has to be in that set over there. And because we were able to conclude that, we could say that A intersect with B union C is contained in, not equal to, but is a subset of A intersect B union A intersect C. There's always like a risk of when you're trying to show that two sets are equal, like when you're finished the first half, it just feels like we've accomplished something, and so we feel like we're done. And we are done with that part of the proof, but there's another whole like half of the problem to do.
Which I know because there's a whole blank page here.
Yeah, we might not need the other page, but depending on how big we write, it could spill over. All right, so that's the first part. How much space do I have? Maybe I'll just start it on the second page so I could do it all in one go. So the second part of the proof is A intersect B union A intersect C contained in A intersect B union C. That's what we're going to prove. How do we start a containment proof? What should our first line be? Okay, something X. Okay, where is that gonna, where, so that's true. Where are we gonna put it? Where are we gonna, not where are we gonna put it, where are we gonna take it from? We're selecting an element from the universe. Where are we making sure that we take it from?
The left side.
The left side. So we're gonna let X be an element of that set on the left. So that's A intersect B union with A intersect C. Where are we gonna, what are we gonna show?
We're going to show that X is contained within A intersect B union C.
X is contained within A intersect B union C. Yeah, we got to put it in the set on the right. Right? So we have to take it from the set on the left, and then we have to show that it must live in the set on the right. So, all right, we have X in the union of A intersect B and A intersect C. What does it mean to be in the union?
It's in one or the other.
Mm-hmm. Yeah. So we could say then X is in A intersect B, or X is in A intersect C. It's got to be in one of those two. Regardless of which one that it's in, where can I for sure say X has to live?
A.
A. Okay, so let's write that down. Great. So now, again, let's keep our eye on the ball. We know we want to put X in the intersection of these two things. We've already got it in one of them. What's my next part that I'm trying to show?
Prove that it's in the other part.
Yeah, so I got to make sure, I got to prove that it's in B union C, which means I need to prove that it's either in B or C, or both. All right, so right now we know that it's in one of these two intersections, A intersect B, A intersect C. So let's just take it case by case, right? So if X is in A intersect B, where do I also know it lives?
B.
Then it has to be in B, right? Because it's got to be in both A and B. So then X is in B. And so X is in, if it's in B, where does it live? It would be an A union B, but that's not what where I'm going here. B union C. It's in B union anything if it's in B, right? And then the helpful thing is to observe it's got to be in B union C. Okay. What if X is in the other set? What if X is in A intersect C?
Means
X is a part of C, and so,
So then X is an element of C?
yeah,
Yep, and what does that mean?
X is an element of B union C.
Yeah. Okay, so now regardless of which two of those intersections it's in, we could say for sure that it's in B union C. We already said it's for sure in an element of A. So X is in A and X is in B union C. And what does that mean? Where does it live?
It lives in A intersects B union C.
Yep. And now that allows us to conclude like this part of the proof, right? That we started with let X be in that proof that's on the left. And then we said thus X has to be in this set on the right. So that means we've shown containment in this direction. A intersect B, union A intersect C must be contained in, whoops, A intersect B union C. And so we've done both parts. What we want to do is just sort of wrap up, like tie up this proof. Like overall, our ultimate goal was to show that the two sets are equal. We've done all the hard work. Let's just write a nice concluding statement, something like,
I'm right.
I'm right. Yep. So when I'm showing two sets are equal, often I'll use a phrase like, having shown containment both ways. It follows. Hey.
Is this a big one?
You mean like the notes for the section? Chapter 2, they're the same notes. Were you here on Tuesday?
Yeah.
Okay, it's the same notes as that one. Yep. It follows that these two sets have to be equal. So A intersect B union C is equal to A intersect B union A intersect C. That's not the only wording, really, kind of add your own language. But you want some kind of concluding statement. Is that fun?
No.
Yeah. Yeah. Okay. There's some proofs that you can write in the practice exercises. I strongly recommend you have a go at those, or at least, have a quick go and look at the solutions to see how I approached it. Wes?
Could you scroll up to the first section again? I missed
Yep.
the sentence.
Yeah.
Right there.
So, because there's a proof that you're going to write on the second assignment, a containment proof. It's a good one. Not just a containment, an equals proof, that you're going to show two sets are equal. No. None of that.
It's just a lot to
Excitement.
write. It's not necessarily awful, it's just a lot to write.
Yeah, we're going to write a lot in this course.
Necessarily awful.
It is necessarily awful? Adam.
I mean,
Enough.
These are all, you're recording these and putting them on Canvas.
Yeah,
right?
yeah,
Gotcha. It's taking so much mental energy
yeah.
to keep up with writing the notes down
Yeah.
that actually absorbing what the notes contain is.
Yeah, so the notes themselves are usually posted by same day or the next morning. The video will be at least the next day and maybe the day after. The problem, I'll tell you why it takes a while to do the video, is because I have to render it on this computer, and rendering takes all of the resources. If I just try to check my email while I'm rendering, it will take 5 minutes to just get to Outlook. So I have to just set it up at night and let them go, and at a time when I know I don't need to use my computer for anything for a while. So that's why it takes a day or two to get those up. But the notes are always up pretty quick. So you can you could start there. And for example, Tuesday's video isn't up yet, but I'm rendering that one and this one tonight, and they should both be up tomorrow. Are there questions? Okay. All right, so that's it for the new stuff. We just finished chapter 2. Just to let you know what's coming down, since we have a few minutes here, our first test will be coming up. This is the second week of classes, right? When's our break week? The week of 20-something? So I think probably on the 20th, if I were to wager a guess, will be when we have our first in-class test and when you'll be turning in the take-home part of the test. Each test has two parts, a take-home part and an in-class part. The in-class part is mostly computational, more computational. So I think there's a good chance we'll have it on the 20th. If not, we could push it till after break, but usually it's better if it works out timing-wise. I always try to do it before the break, Yeah.
Are we gonna have to write any proofs in class?
I'll talk about that later.
That was the same question.
Yeah.
I'll be here all week.
So just kind of stick a pin in that. We're getting ready to have our first test. On Tuesday, we'll start chapter 3. The first test material is chapters 1 through 3. They're all kind of neatly tied together. We're going to look at Boolean algebra and sort of see how Boolean algebra ties together concepts of logic and set theory. And yeah, so I'm just going to put this out here. Probably. You'll have at least a full week, probably longer, with the take-home test. I will also hand out a practice in-class test, and my solutions to that will be available. It's mostly computational, like things like find the intersection of these sets, or make a truth table and show these are whatever. There's some cool stuff that we're going to do with binary representation of numbers, and you will write a proof. But the way it's set up is that like when I give you the practice in class, at the end there's going to be like write a proof, and there's going to be 4 proofs to write. Not that you're going to write 4 proofs, but there's 4 things.
You can choose one.
Yeah. So what happens is I'm going to pick 3 of those, and say pick one of these 3. So if you could do any 2 of the ones, if you could do at least 2 of the 4,
You're guaranteed.
then you're guaranteed to be able to find one that you can do on the in-class. And then there's a bunch of proofs you're going to write on the take-home. Don't worry. You're going to get lots of proof writing to do. Okay. So let's see. I've got assignment 2 to hand out. We're going to use the rest of class time today. If you haven't finished assignment 1 yet, work on that today. If you have finished assignment 1, you get a start on assignment 2, or the practice.